We did some good heavy-duty thinking here. We said that if you're in an orbit, the key idea is that gravity is what's pulling you in a circle. If I'm in orbit, if the question mentions orbits, that's almost the first thing I write down, right up there with if there's a projectile, T-tables. If there's forces, free body diagram. If I'm in orbit, gravity is what's pulling me in a circle. For gravity, I have to make sure I use the cosmic gravity equation, big G, big M, little m over r squared. For circular motion, it's going to be mass times circular acceleration. Which one? It depends whether they ask for or give me the speed or the period. And I said there were three variables, three things we can find in orbits. Your orbital speed, your orbital radius, and your orbital period. If I give you any one of them, you can find the other two. We did notice that in orbit, the little m, the little mass, the orbital mass, canceled. Once you're in orbit, doesn't matter what your mass is. The original Star Trek series took some heat for this. One of the classic plot lines in the original Star Trek was where the Enterprise was in orbit, the engines are failing, and so if Scotty doesn't repair the engines, they're going to crash into the planet. Well, they won't. If you're in a stable orbit, our satellites don't all have little rocket engines to keep them up there. Once they're up there, they're fine. The Star Trek The Next Generation, they fixed that. They never used that as a plot line. In fact, you never saw the whole, our engines are going to fail, orbits are decaying, we're going to crash into the planet as a plot line for any of the newer series. But in the first one, they did. And they took some heat for that from nerds. So they learned. Fight the nerd power, right? We proved that the gravitational field in orbit and the acceleration, circular acceleration in orbit were the same, which meant, actually, if you're in orbit, you're in free fall. We talked about why astronauts are weightless. We even calculated how fast you would need to travel to orbit right at the Earth's surface. It's calculatable. And we started looking at example 5. By the way, I like example 5. Example 5 is fundamental to what we're going to be doing on rocket science. So in example 5, I gave you the period in minutes, multiply it by seconds. So Drake, example 5 would be, let's suppose I want a satellite to orbit the Earth every, 900 minutes, every 10 hours, every 8 hours, if I had it every 24 hours, we call that a geosynchronous orbit because it's orbiting and staying above the same place on the Earth the whole time because it's spinning at just the right velocity so that it matches above the Earth at the same time. All geosynchronous orbits have the same period, 24 hours. We can figure out how high we want to put it or how fast it needs to be traveling. So we found the altitude. We did talk about the difference between altitude and orbital radius. The altitude is the orbital radius minus the radius of the Earth. Usually I'll just ask for the orbital radius, but in the quote-unquote real world, typically they'll want or give you the altitude because typically we measure how high above the Earth. And we paused here. Rebecca, what does B want me to find?
Orbital velocity.
What kind of velocity?
Orbital.
Are you saying we're in orbit? Well, that means that gravity is what's pulling me in a circle. And gravity is always big G, big M, little m over r squared, which r? Orbital r. And that's going to equal m. Oh, they want orbital speed? V squared over r orb. Does an r cancel this time? Yeah. This time that r would move up to there and that r would cancel with one of the r's. So I typically cross out the r on the right and the squared. Please notice an r does not always cancel. In the example we did at the end last class, we found we ended up with an r cubed. We actually had to cube root. It was kind of nice. We found a use for cube root. Mass of the satellite cancels. In fact, I end up with v squared equals big G, big M over r, or v equals the square root of big G, big M over orbital radius. Do I know big G? This is the conversion factor, if you will. This is what you need to multiply kilograms per meter squared by to get newtons. It's the 6.67 times 10 to the negative 11. I have a video explaining where that came from, but I'm just trying to do a search to find a more modern one, because the one that I have is about 7 years old, before YouTube went to HTML, went to HD. So bear with me. I'm trying to find a better one if I can. 6.67 times 10 to the negative 11. Big M is the mass of the planet that we're orbiting. Are we orbiting Earth? In fact, if the question doesn't specifically mention a planet, Sinead, let's assume we're always Earth. But I will, on your test, at least once, just for giggles, have you do something on the moon or another planet, because I dream. Mass of the Earth is 5.98 times 10 to the 24th, right? Now, this question didn't give me our orbit, but what did I calculate in the previous question? Altitude, but right there I also wrote down the orbital radius. So on the bottom, 148.48096. And this will give me the orbital speed. And again, I strongly encourage you, practice typing these in. I told you when we're talking about the Earth, typically your orbital speeds will be in thousands of meters per second. So I'm not creeped out by that answer. I get 5.18 times 10 to the third meters per second, 5,180 meters per second, 5.2 kilometers every second, and that'll keep it going. Looking at what I wrote here, so if you know the orbital radius, you can get the speed. If I had told you the speed, could you also have found the orbital radius? You'd get that by itself. You'd start out with the v squared equation, but I think you'll end up with big G, big M over v squared is the orbital radius. And up here, I told you the period, and we found the radius. Back here, I told you the radius, we found the speed. As I've said, there's three main things in orbit: orbital radius, orbital speed, orbital period. Any one you can find the other two. Oh, and then if they ask for an altitude, subtract the radius of the planet to get the altitude. I guess if we want an equation for orbital period, again, this is not on your formula sheet. I've never bothered memorizing it. I derive it. Gravity is what's pulling me in a circle. Big G, big M, little m over r squared equals m4 pi squared r over t squared. Cancels. Does an r cancel this time? No. Think about it. The r squared's on the bottom on the left, but it's on the top on the right. When you moved it from the right to the left, it would become an r cubed. In fact, let's draw a little line right down the middle of our box. We're going to do two equations. We're going to get an equation for period. Let's see if we can do it in our heads. The t squared would move to the top, yes? The big G, big M would move to the bottom. And then the r squared would move to the top on the right, but there's already an r there. I think we would have this, a 4, a pi squared, and r cubed over big G, big M. Now really, that's t squared. How to get rid of a squared? Don't memorize it. We can derive it. What if we wanted to get the r by itself? Well, the r squared would move to the top on the right and give, well, just to make it easy in your mind, start here, times the gm over, yes? Divide the 4 pi squared over. That would give you an r cubed. How do we get rid of a cubed? Okay. Wow, that really jumped back all of a sudden. So it's going to be, is right, whoever said that, the cube root of big G, big M, t squared all over 4 pi squared. I think that's what we wrote back here too, did we not? Yeah, there it is. Big G, big M, t squared over 4 pi squared. Again, Julie, you want to memorize those? Knock yourself out. I just can't be bothered. I'm pretty good at cross multiplying, which is really what we're doing. These are your equations. Questions that you're now, oh, I do have a couple more. One more. Cool. Put your pencils down, look up. We'll finish with example 6. I like example 6. I like example 6. Example 6 is a nice question. Hey, remember I told you there was 3 things that we could find, Julie? Here's all 3. A says what's its orbital radius, B says what's its orbital velocity, C says what's its orbital period. What did I give you here? I gave you its altitude. Don't give me altitude. No, that's don't give me attitude. I gave you its altitude. If you're wanting a visualization, we can do a little DULP here. What I've given you is this distance here, and I've told you it's 1.2 times 10 to the 6th. There's the satellite. What does A want me to find? No? What does A want me to find, Connor?
Orbital radius.
How can I find orbital radius? Now, just again, in my picture, that's the orbital radius. And that's the one we need to use in our equations. How can I figure out how big it is, how far it is from the center of the Earth to where the satellite is? Okay, so the orbital radius is going to be the radius of the Earth or the moon or the sun, whatever planet you're orbiting, plus the altitude. It's going to be 6.38 times 10 to the 6th plus 1.2 times 10 to the 6th. Actually, since these are both 10 to the 6th, I could probably add these in my head. It's going to be 6.38 plus 1.2, 7.58 times 10 to the 6th. Double check me, but I'm pretty sure that'll work. If they're not 10 to the 6th, if the scientific notation powers don't match, you got to be a bit more careful doing it in your head, but if they match, I can just add the numbers like they're regular numbers. It is 7.58 meters. Lindsay, what if I wanted to convert that to kilometers? How would I do that? Divide it by 1,000. I've had some students, you're not the only one, in my other classes as well. Isn't it 3.6? That's if it's meters per second or kilometers per hour. Here it's straight distance. It's either going to be times by 1,000 if they give it to you in kilometers, which in the homework they do, or divide by 1,000 if they ask for it in kilometers, which I think once in the homework they do. There's part A. Brandon, what does part B want me to find?
Orbital velocity.
Duncan, what does part C want me to find?
Orbital period.
You know what? Let's do these side by side just so we can see how they look very similar. Let's do part B here and part C here. What kind of velocity? Orbital. What kind of period? Orbital. You're saying we're in orbit? Well then, gravity is what's pulling me in a circle. Gravity is what's pulling me in a circle. That would be our free body diagram, except to me, since there's only one force, I didn't draw a free body diagram. It's gravity. Big G, big M, little m over r squared equals, and I guess for orbital velocity, I'll use mv squared over r. Big G, big M, little m over r squared. I guess for orbital period, don't forget the m, for pi squared r over t squared. Some stuff cancels in the first equation. What cancels in part B? Little m's. Got to be fussy because there's more than one m. Little m's. And here, one of the r's cancels because the r's are all on the bottom. On the right-hand side, though, although the m cancels, the r does not, James, because it's an r squared on the bottom on the left and it's an r on the top on the right. They're not on the same level. We can't make that assumption. Oh, I already got the v by, well, I got the v squared by itself. So v orb is going to be big G, big M over r orb. Not the altitude, the radius. Here, oh, we want to find t. So it's going to be a 4, a pi squared, an r cubed, divided by big G, big M, square rooted. I think that's what we had in our box as well, but again, I never bothered memorizing it. If you haven't figured out, Nick, when you have one fraction equals one fraction, which is what we have, stuff moves diagonally. Play around with it, but that's really what cross multiplying is. Okay, it's plug and chug. Complicated plug and chug, especially on the right-hand side. Again, I really encourage you. I'm going to say you guys try this the rest of the way on your own. I'll do it up here. Practice typing these into your calculator. See if we end up with the same answers. Normally, I'd freeze my screen so you couldn't just copy from me, but this loaner projector doesn't have a freeze button, so I'll just have to do this. By the way, some of your scientific calculators might have some constants programmed in if you look at the inside cover of your calculator case. Some calculators do have big G pre-programmed, not the graphing ones, but I think some of the TIs do. Maybe it was one of the Casios. I can't remember, but I've had some calculators in the past. They actually have the mass of the Earth pre-programmed in, and you actually have a constant button. So you constant button 1, constant button 5, constant button whatever. What was it, 7.58? I would have caught that, honest. Well, I would have fixed it on my next line probably regardless, because I do have the habit of asking at the end, what was I finding? Units, right? Those are the two things my brain tends to check. All right. You get 7,250 for the velocity. By the way, I guess technically it's an orbital speed because I didn't give a direction. I'm ignoring you. Hang on. Sorry. Now I'm listening. Well, for the velocity, tangent to the radius. If it was an acceleration, toward the center. If it's a period, it's a scalar. Clockwise is totally irrelevant because it depends on whether you're looking from above or from below, and there's no reason. I mean, even north being up is technically wrong. What the? Oh, square root. Whew. You get 65, 65? Divide by 60. Yeah, 109 minutes times. Okay. I know that basically, well, we calculated the period if you were orbiting right at the Earth's surface was like 84 minutes or something like that, I seem to recall. As you go further away, the period does lengthen. As you go further away from the Earth, what happens to the velocity? The orbital speed gets smaller as r gets, look at the equation for v. As r gets bigger, your speed gets smaller. But you need way more energy to get it up that high in the first place. So it's not cheaper to put stuff further away, sadly. The amount of energy it takes to get it up there far outweighs the amount of energy to get it spinning. How much kinetic energy would this object have? You need to know the mass of the satellite, but it'll be a half m times this v squared. And that kinetic energy also comes from the rocket fuel. So you got to make sure you got enough rocket fuel to do that too. Meanwhile, let's write the answer down. The period was 65, and I guess it would be 70 because there was a 5 next to it. Yes, technically? Seconds. Orbits. So I said you could try 1, 2, 3, 4, 5, 6. We can add number 7. A geosynchronous orbit is one where it stays above the Earth at all times. Its period is 24 hours times 60 seconds times 60 minutes. What's the radius? You're going to find any geosynchronous orbit, they're orbiting at the same speed and the same radius. GPS satellites are geosynchronous. Many of our communication satellites are geosynchronous. There is, because it's such a huge circle, the circumference of that circle is so big, there's still lots of room up there. But if you want the satellites, for example, to permanently stay above, well, they stay above locations on the equator also, because they're orbiting at the same speed right along the equator. So if you want one of your satellites to stay right above the city of Quito, which is really close to the equator, basically on the equator, there's only room for so many satellites right above that city before it's getting crowded. But there's still lots of room for geosynchronous ones. 9 is good. Imagine, do I want to do 8? Imagine an asteroid X revolves around the sun with an orbital radius. Draw 2 or more conclusions about the orbit of... I didn't include the answers, so okay. 10 is tricky. This is how clever you are. What I've given you in number 10 is the gravitational field strength on the Earth, little g. $12. Skip 11. 13. He already has, thanks. 14. And 15. In number 12, I give you the speed and I say find the period and the height and the radius. In number 13, I give you the height and I say find the radius, the period, and the speed. In number 14, I give you the period and I say find the height, the radius, and the speed. It's all going to start out by going, gravity is what's pulling me in a circle, because I'm in orbit. I was going to go over the tests, but I'll give you time to work on this. I got carried away on cool videos.